Increasing and decreasing. Our objective is to use the derivative to determine where a function is increasing and decreasing. The following are corollaries to the mean value theorem, which means they come from using the mean value theorem. Increasing, decreasing function test. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0 for all x in the interval, then f is increasing on that interval. If f prime of x is less than 0 for all x in the interval, then f is decreasing on that interval. And if f prime of x equals 0 for all x in the interval, then f is constant on that interval. Examples. Determine where each function is increasing or decreasing. Justify your answer. So to do this, we're going to use the derivative. Let's start with taking the derivative of h of x. H prime of x is 4x cubed minus 12x squared. Now to see where f prime, the derivative, is positive or negative, we need to figure out first where it's 0 or doesn't exist. In other words, we need to find the critical numbers. So to do that, let's set our derivative equal to 0. I notice there's no place it's going to not exist, so 4x cubed minus 12x squared equals 0. I can factor 4x squared out, and x minus 3 is left, and I've got two zeros, x equals 0 and 3, two critical numbers. Let's draw our sign chart or number line. Let's mark off that we are going to list the intervals on top and the sign of the derivative h prime on the bottom. Let's mark off where our critical numbers are, 0 and 3, in the order that they would appear. So, not given any closed interval, we'll make our first interval go negative infinity to 0, then 0 to 3, then 3 to infinity. Now we're trying to find the sign of h prime, the derivative. So somewhere on this interval, let's think of a test value we can plug in. From negative infinity to 0, how about negative 10? Something big, something that would be easy to evaluate positive or negative. I like to use the derivative form that is factored. So this one up here is factored. This factor will always be positive. Plugging negative 10 in here makes a negative, and a positive times a negative is a negative. I don't care about the value, I just care about the sign. That sign is negative. On the next interval, from 0 to 3, I can pick a test value like 1. Again, that one is positive. 1 minus 3 is negative. I don't care the value, I just care the sign. And a positive times a negative is a negative. Finally, on that interval from 3 to infinity, I'll pick something large, maybe 10, maybe 100 if I want to. Again, that's positive. This factor makes a positive, and a positive times a positive is a positive. Now we'll look back to our information about the increasing and decreasing and use our signs to help make conclusions. So we see that the function will be increasing on this interval because the derivative is positive. So for our conclusion, we'll say that h of x is increasing on the interval 3 to infinity. Let's remember to justify our answer using our derivative. This sign chart is just our work. It is not enough justification by itself. We use it to write our justification. So h of x is increasing on the interval 3 to infinity because h prime of x is greater than 0. How about where h of x is decreasing? Notice it's decreasing. Well, the derivative is negative on this interval. The derivative is negative on the interval right next to it. At 0, There's nothing happening such as any domain restriction because this is a polynomial, so we can join these intervals and say the function is decreasing right through from negative infinity to positive 3. So we'll say on the interval negative infinity to positive 3, and our justification because h prime of x is less than 0. 2. We'll find here where g of x is increasing or decreasing using the derivative. G of x equals 1 over x squared plus 2x. Now I notice there's a denominator, so we probably are going to have some sort of domain restriction because our denominator can't equal 0. So where does x squared plus 2x equal 0? Factoring out x, it looks like it's where x equals 0 and negative 2. Now this makes the denominator 0, but the numerator doesn't have any common factors. So these restrictions are vertical asymptotes. Let's make that note there to help us when we get down to our sign chart. Now we need the derivative of g of x to find our critical numbers. I'm going to first rewrite this. Because our numerator is just a constant, I don't need to use the quotient rule. Although I can, I would prefer to bring up the denominator and use the chain rule. So now I can find g prime of x, negative 1 times x squared plus 2x to the negative 2 times the derivative of the inside, 2x plus 2. That can be rewritten as negative of 2x plus 2 over x squared plus 2x squared. To find our critical numbers, we'll look first where g prime of x equals 0. Given a rational function, that's going to be where the numerator equals 0, and that gives us x equals negative 1. We also want to know where our derivative does not exist. That's going to be where our denominator equals 0, and that gives us the values from where we saw the vertical asymptotes, x equals 0 and negative 2. Now, because these are already domain restrictions, these are not critical numbers. But they still are going to indicate starts and stops of our intervals because they are starts and stops of the graph because of the vertical asymptotes. So let's go ahead and make our sign chart where we indicate our intervals on top and our sign of the derivative of our function, g prime this time, on the bottom. We've got 0, negative 2, and negative 1 that we have to chart. Let's make sure we put them in order. Negative 2, then negative 1, then 0. So our first interval goes negative infinity to negative 2, then negative 2 to negative 1, negative 1 to 0, and 0 to infinity. It's also helpful to note in the sign chart that we have a vertical asymptote at 0 and negative 2. So I'm going to note that. Now we can find the sign of the derivative. Let's pick a test value between negative infinity and negative 2. How about negative 10? We'll go to our derivative. This form is probably the best one to use. I notice that because the denominator is squared, it will always be positive. Our numerator, though, will change depending. So plugging in negative 10 in here, I get a negative, but then I take the negative of that negative, and that makes a positive. On the next interval from negative 2 to negative 1, I probably need negative 1.5. I plug that in here, get a negative times a negative makes a positive again. Remember, I'm ignoring the denominator because it's already just positive. Plug in a value between negative 1 and 0, such as negative 1/2 or negative 0.5. That makes a positive here, times a negative makes a negative. And then a test value between 0 and infinity, maybe 10. Plugging that in here is a positive, times negative 1 is a negative. And now I've completed my sign chart. Let's use this to draw our conclusions. Now, in the previous example, when we had two intervals next to each other, we joined them, going from maybe negative infinity to -1 if that were the case here. We cannot do that in this example because there is a break in the graph by a vertical asymptote. So we will say here that g of x is increasing on the interval negative infinity to -2, stopping at the vertical asymptote, union, starting up right after it, -2 to -1, and we will, of course, justify our answer with the derivative because g prime is greater than 0. G of x is decreasing on these intervals. Again, we have to stop where there's the vertical asymptote. So -1 to 0, union 0 to infinity, because g prime is less than 0, or g prime is negative.